Welcome to AI Peer Review, the deep dive that gives you the sharpest insight into the research shaping clinical technology.
Glad to be here. Today, we're looking at a really interesting paper that's trying to solve a pretty fundamental problem in gastroenterology.
Which is?
Automated reporting and, maybe more importantly, quality assurance in colonoscopy. And they're doing it using computer vision.
Okay, right. Colonoscopy. Let's set the stage a bit because the stakes are high here. This procedure is absolutely critical for catching colorectal cancer early, potentially preventing it altogether.
Exactly. But the quality of that colonoscopy matters immensely. It's not just about doing it, it's about doing it well.
And there are standards for that, right? International medical societies, they push for monitoring specific quality indicators or QIs.
That's right. Things like the adenoma detection rate, how often polyps are found, and really key for this paper, the withdrawal time.
Ah, yes, the withdrawal time. Remind us of the target there.
So the standard is ideally 10 minutes, but an absolute minimum of 6 minutes. That's the time the doctor spends slowly pulling the scope back out.
Giving them time to really inspect the colon lining.
Precisely. But here's the problem this paper tackles. Checking that withdrawal time, figuring out which part of the colon the scope was in, how long it's spent there. All of that is currently manual.
Someone has to actually watch the video recording afterwards. That sounds incredibly time-consuming.
It is. Often lengthy videos, too. So the goal here, the gap this paper tries to fill, is building an AI system for autonomous temporal segmentation.
Meaning the AI automatically breaks down the entire video recording?
Yep. Breaks it down into the different phases of the procedure, like insertion, withdrawal, and also identifies which anatomical section of the colon is being viewed at any given time.
Instantly providing all that quality reporting data.
That's the idea. And this specific task, segmenting the entire procedure video temporally, hasn't really been cracked before, partly because there weren't good public benchmarks.
Which this paper actually introduces, right? They built a benchmark.
They did. They took an existing public data set called Real Colon, which has 60 complete colonoscopy videos.
Okay.
And they meticulously annotated every single frame. We're talking 2.7 million frames in total.
Wow.
And crucially, they've made these annotations open access. So now there's a standard data set for researchers working on this specific problem.
So what does the segmentation task look like? How many categories are they trying to identify?
It's a 9-class segmentation task. Pretty detailed.
9 classes. Okay, what are they?
Well, you've got 3 main procedural phases: outside the colon, before or after the procedure proper, then insertion, going in, and withdrawal, coming back out.
And the other 6 must be the anatomical location.
Exactly. The 7 distinct segments, starting from the deepest point, the cecum, sometimes the ileum just beyond it, then ascending colon, transverse, descending, sigmoid, and finally the rectum near the exit.
That's quite granular. And you mentioned the videos themselves present challenges.
Oh, definitely. The variability is huge. First, the length. The shortest video is around 11 minutes, but the longest, get this, 82 minutes.
82 minutes.
For one procedure.
Yep. Longer than some movies. The average is about 28 minutes, even sampled down to 5 frames per second. That's still a massive number of frames per video.
Trying to model temporal dependencies over an 82-minute span? That sounds computationally brutal.
It is, and that length variability feeds into the second major challenge: severe class imbalance.
Meaning some of those 9 classes appear way more often than others.
Exactly. Like, frames outside the colon are relatively rare compared to the time spent inside. But even inside, there's imbalance. Think about the ileum.
The bit just past the cecum.
Right, it's the target endpoint, but
Yeah.
it wasn't even reached in 34 out of the 60 videos. So the model has very few examples of what the ileum looks like compared to, say, the sigmoid colon.
So the model has to be good at recognizing really long, common phases like insertion, but also these super short, potentially rare segments like the ileum, if it even appears.
Precisely. It has to handle both extremes. Okay, I can see why standard approaches might struggle. You can't just feed an 82-minute video into any off-the-shelf vision model, especially not the ones that have been dominant recently, like transformers.
You really can't. Models like ASFormer, which is a strong baseline using transformers for action segmentation, hit a fundamental scaling issue here.
The attention mechanism, right.
Exactly. Self-attention, which is the core of transformers, scales quadratically with the sequence length.
So double the video length, quadruple the computation.
Pretty much. For sequences spanning tens of thousands of frames, like in these hour-plus videos, the computational cost and memory requirements just become prohibitive. Training and even running inference gets incredibly expensive.
So that pushes the researchers towards a different family of models, temporal convolutional networks, or TCNs.
Right. TCNs use convolutions instead of tension, so they avoid that quadratic scaling problem. They have a lineage going back to earlier sequence models like RNNs, but TCNs are generally better at handling longer dependencies than basic RNNs.
But even standard TCNs have limitations when you're talking about sequences this long, don't they? Like the Techno model mentioned in the paper.
They do. To get a large enough receptive field, meaning to allow the model to see context across the entire 80-minute span, a standard TCN needs to stack a lot of convolutional layers.
And you use dilation in those convolutions to help expand the view.
Yes, dilated convolutions are key. They allow the kernel to skip inputs, effectively looking at a wider range. But to cover an hour-long video, you need many, many layers with increasing dilation factors.
And stacking that many layers causes its own problems.
It can, yeah. Very deep networks can suffer from vanishing gradients during training. The error signal struggles to propagate all the way back through that huge stack of layers.
Making it hard for the model to actually learn those long-range dependencies effectively.
Exactly. Training becomes unstable, and the performance might not be great. This limitation is really the motivation for the custom architecture proposed in the paper. TCN.
Okay, so let's get into TCN. How does it overcome this issue? How does it manage to get that huge receptive field needed for an 80-minute video without becoming untrainable?
The core idea is in their custom building block, which they call the temporal block, or TB. It's designed to be much more efficient at capturing temporal information while still being easy to train, even when stacked deeply.
What's different about this temporal block compared to a standard TCN layer? Conceptually, like what's shown in their figure 4.
The main innovation is the use of double-dilated residual convolutions.
Double dilated, what does that mean?
Okay, think of standard dilation. A kernel might look at every, say, third frame. Double dilation means it effectively looks even farther apart, maybe every sixth frame. But using two convolutional layers within the block, each dilated, it lets them expand the receptive field faster per block.
Ah, I see. So you get more temporal coverage with fewer blocks or deeper coverage with the same number of blocks.
Kind of, yeah. It's about efficiency in expanding that view. And critically, they pair this with a residual connection within each block.
The standard ResNet trick, basically, adding the input of the block to its output.
Exactly. That residual connection is famous for helping gradients flow through very deep networks. It combats that vanishing gradient problem we talked about.
So the residual connection lets them stack more blocks deep.
Right. They found that 12 or 13 blocks worked optimally.
And the double dilation within each block makes sure that deep stack efficiently covers the whole video's timeline.
Precisely. It's that combination. Plus, they add dropout regularization, a rate of 0.5 after each convolution within the block.
Standard practice to prevent overfitting, especially with potentially variable video styles.
Yep. Helps stabilize training and improve generalization. So double dilation plus residual connections plus regularization is the recipe for their temporal block.
Okay, that makes sense for the core architecture. What about handling the input features and the prediction task itself, like the loss function, especially given that class imbalance?
Good question. For input features, they used a standard approach. Extract features from each frame using a ResNet 50 pre-trained on ImageNet. Then they use a simple one-by-one convolution, what they call a feature reduction layer, just to reduce the feature dimension before feeding it into the TCN.
Makes sense. And the loss. Predicting one of 9 classes, some very rare.
Yeah, the loss function had to be tailored. It's actually a combination of 2 loss terms.
Okay.
First, a weighted cross-entropy loss. This is pretty standard for classification. The weighted part is key, though. They use median frequency balancing.
Which means the rarer classes, like the allium, get a higher weight in the loss calculation.
Exactly. It forces the model to pay more attention to getting those infrequent but potentially important segments right.
And the second part of the loss?
That's a truncated mean squared error, or LTMSE. This one is interesting. It's designed to tackle over-segmentation errors.
Over-segmentation. Like the model flickering rapidly between predicting, say, ascending and transverse colon.
Precisely that. The LTMSE term penalizes those rapid changes, encouraging smoother, more stable predictions across time. It helps ensure that if the model thinks it's in the sigmoid colon, it stays predicting sigmoid for a reasonable duration, not jumping back and forth every few frames.
Right, making the output boundaries more robust. Okay, so we have the data, the model architecture, the loss. Let's talk evaluation. How did they test TCN, especially against those challenges like generalization?
They used a pretty rigorous setup with a dual K-fold cross-validation protocol.
Dual protocol.
Yeah, two different ways of splitting the data. First was a standard 5-fold cross-validation. Here, you use 4 folds for training, that's 44 videos in this case, and 1 fold for testing, rotating through. This maximizes the training data for each run.
Good for assessing overall peak performance when you have more data. What was the second protocol?
The second one was tougher. A 4-fold cross-validation designed specifically to test generalization.
How did that work?
Here, they trained on fewer videos, only 3 folds, so 30 videos. And crucially, the test fold consists of videos from unseen medical centers.
So different hospitals, potentially different equipment, different continents even.
Exactly. This really tests if the model learned generalizable features or if it just overfit to the style of the clinics it saw during training. A much harder but more clinically relevant test.
Makes sense. And what metrics did they use to measure success in these scenarios, especially considering the class imbalance and the clinical importance of things like withdrawal time?
They used a few key metrics. For overall segmentation quality, they reported weighted F1 score, WF1, and weighted Jacquard index, WDRAKE.
Weighted again to account for those rare classes.
Right. These give more importance to correctly classifying the less frequent segments like the ileum, giving a fairer picture than just accuracy.
And for the clinical side?
The most critical one was WMAPE, withdrawal mean absolute percentage error.
So how far off, percentage-wise, was the model's prediction of the withdrawal phase duration compared to the ground truth?
Exactly. This directly measures how accurately the model estimates that key quality indicator. A lower WMAPE is better.
Okay, the moment of truth. How did colon-TCN perform against the beater lines like the Transformer ASFormer and the standard TCN Techno, especially its multi-stage version MSTCN?
It did very well, particularly considering its efficiency. One key finding was that colon-TCN used significantly fewer parameters, about half as many as the multi-stage MSTCN baseline.
Half the parameters. That suggests the double-dilated temporal block is indeed quite efficient.
It seems so. And performance-wise, in the standard 5-fold setup, more training data, colon-TCN came out on top. It achieved the highest weighted F1 score at 76.4 and the highest weighted Jacquard at 65.0.
So best peak performance. But what about that tougher generalization test, the 4-fold cross-validation on unseen centers? That feels like the real acid test.
And that's where colon-TCN also shone. It again achieved the highest weighted F1 score, 62.9, and really importantly, the lowest WMAPE for withdrawal time prediction at 16.2%.
Lower error in predicting withdrawal time, even on data from totally new environments. That's significant.
It really is. It shows the features learned by colon-TCN, likely thanks to that temporal block design, are more robust and generalize better across different clinical settings compared to the other approaches, even when trained on less data.
Now, you mentioned multi-stage TCNs like MSTCN. Often, in temporal segmentation, people use refinement stages. An initial prediction pass, then another pass to clean up the boundaries. Did colon-TCN use that?
They tested it. They built a multi-stage version, MS colon-TCN. But here's a really interesting finding from their ablation studies.
Okay.
The multi-stage version, MS colon-TCN, did not perform better than just using a deeper single-stage colon-TCN with more temporal blocks.
Wait, really? So adding refinement stages didn't help? That seems counterintuitive for precise boundary detection.
It does seem a bit counterintuitive, right? But think about the nature of this task. You have these incredibly long, mostly stable segments, like the entire insertion phase, which might last 30 minutes. The implication seems to be that for this specific problem, getting the global context right reliably, knowing you're still in the insertion phase after 25 minutes, is more critical than slightly refining the exact frame where insertion switches to cecum.
So the deep single-stage colon-TCN, maybe with 12 or 13 blocks, was better at maintaining that long-range consistency across the whole 80-minute video.
That seems to be the conclusion. Efficiency in capturing the global picture in one strong pass trumped iterative refinement for this particular domain. They didn't need to fix lots of small errors. They needed a model that just didn't get lost over the long haul.
Fascinating. So summing up the impact, what does this mean for clinical practice? We have a model, colon-TCN, that's efficient and robustly segments entire procedures.
It demonstrates pretty clearly that automated temporal segmentation for full colonoscopies is feasible. It can run offline after the procedure and accurately estimate those key QIs like withdrawal time and even cecal intimation rate confirmation.
Which could automate a lot of the current manual auditing and reporting work.
Exactly. It paves the way for standardized, quick QI reporting, potentially improving feedback loops for clinicians, and making quality assurance much more efficient.
And presumably, integrating it isn't too complex, especially since detecting the outside phase, the start and end, is likely the easiest part.
Yeah, the paper notes that outside is the easiest class to predict, which helps anchor the whole segmentation. So integrating this as a post-procedure analysis tool seems quite practical.
Okay, so that's the current state powerful offline analysis, but you hinted at a future direction. Let's talk about that.
Right, so the current colon TCN model uses a causal convolutions.
Meaning, to predict the label for frame T, it looks at frames both before and after T.
Correct. It uses future context, which is perfectly fine for analyzing a completed video recording offline.
But not useful if you want the AI to provide feedback during the procedure itself.
Precisely. For real-time applications, maybe highlighting suspicious areas based on withdrawal speed or tracking milestones as they happen, you need causal convolutions.
Where the model can only use information from the past and present up to frame T to make its prediction for frame T.
Exactly. No looking ahead.
So here's the final thought to leave our listeners with. Given how well colon TCN, even in its acausal form, handles these incredibly long and complex videos, and knowing that the start endpoints are relatively easy, how big a leap is it really to adapt this architecture?
To make it causal.
Yeah, to create a version that could work in real time. What would that unlock? Maybe a real-time guidance for polyp detection or automated tracking of which segment the scope is in as the doctor navigates?
That's the provocative question, isn't it? Moving from post-hoc analysis to real-time assistance. It feels like this work brings us a significant step closer to that possibility.
A really exciting prospect for the future of AI and endoscopy. Thank you for walking us through this deep dive.
My pleasure. It's definitely a compelling piece of work with clear potential.